Hey guys, Miss Marusik here, and in this video we're going to be talking about intermolecular forces and how they tie to solubility. Both the new intermolecular forces that I could form in a solution, as well as talking about how intermolecular forces could prevent solutions from forming in the first place. So we're going to actually start off our discussion with a quick mention about gases. Hopefully we remember that with gases, all of our intermolecular forces have been totally broken. And so what that means is that regardless of what kind of substances I have, gases are always going to dissolve in each other. No matter if they originally had whatever kind of intermolecular forces, because they've been broken, those gases can intermingle with each other and I won't have any kind of issues. So really, when we're going to be talking about intermolecular forces and solubility, we're going to mainly be referring to solids and liquids and how they would dissolve in each other. So to bring us to that, it says here, when solutions are formed, there are three kinds of interparticle interactions that are involved. And if you notice on this picture, it kind of shows us what's happening here. First off, I would need my solute to break apart, and hopefully we remember that it takes to break, so that would be an endothermic process. Our solvent would also need to break apart. That too is an endothermic process. So you notice that I put that both of those would have a positive delta H value. And then here what would happen is once I put those two things together, new intermolecular forces would form. And that would be an exothermic process and have a negative delta H value. Now, once we get to thermochemistry, we're going to talk a little bit more about the importance of these heat values. But for now, what I want us to understand is that this is what happens if a solution forms. But if a solution doesn't form, there must be something about this setup that's hindering that process. And it's all about what strength of intermolecular forces originally existed. If either of these attractions were stronger than the new attractions I'm forming here, those substances would rather remain as the original ones and not make a solution. But then if this new attraction that I'm forming is stronger than either of these original ones, then I would want to make that solution. I kind of joke about this in terms of dating. So let's say I'm dating somebody and I'm attracted to them, but then my celebrity crush comes by. My celebrity crush happens to be Chris Evans. So if Chris Evans, Mr. Captain America himself, walks by and he's attracted to me, and I'm attracted to him, and I'm way more attracted to him than whoever I'm dating, let's be real, probably going to dump whoever I'm dating and go be with Chris Evans. I know that's kind of ridiculous, but it gets the point across that I'm going to only break apart the original attraction if I'm going to form something that's stronger than what I started. If whatever I would have potentially formed is weaker than where I started, then I'm going to keep dating whoever I'm with. I'm going to keep that original attraction that I had. I always want to maintain the stronger interaction. Okay. Now, sometimes it's not a matter of being stronger or weaker, but maybe just that it's being similar in attraction. Okay. So it says here, if the new interactions that are formed are comparable or similar in strength, maybe perfectly the same or maybe just a little bit stronger to the original ones, then the two substances are more likely to dissolve in each other. And you notice it used to do two words here. You could say that they're soluble in each other, or you could say that they are miscible with each other if you have two liquids. If the new interactions that would have been formed are much weaker than the original attractions, then the two substances are more likely to not dissolve in each other. And at that point, we would say that they're insoluble or immiscible. So you notice here, kind of bolded, starred statement here. It says substances with similar intermolecular interactions tend to be miscible or soluble in one another. You want to make sure you commit that to memory. If we have substances that have very different intermolecular interactions, where the new one would be a lot weaker than what I've started, then I'm likely to not be soluble in each other. Now, one other statement here. The stronger the newly formed solute-solvent interactions are, the greater the amount of solubility will be. The more attractions that exist in that new combination, I could have more dissolve than, say, if the new attractions were only slightly stronger. So that can really impact how much it would take to, say, saturate a solution. If the attractions that are forming are really, really strong, it might take a lot to saturate that solution. I can dissolve a whole bunch in that solution. But if the new interactions are only a little bit stronger than where I started, then I might not be able to dissolve quite as much. All right, so let's go ahead and look at the next page. Now, the next page has kind of a flow chart thing here, where I actually want to start with the substances that are in the middle. And so what I've presented you here with are the original substance types that we could have. We could have an ionic compound, a polar covalent compound, or a non-polar covalent compound. And so the first thing I did is I went and identified the dominant attraction types that I would have for each of those substances. For ionic bonds are the dominant attraction. And as we know, that's a really strong attraction because, again, we're referring to a bond versus just a force. Polar covalent would either be dipole-dipole or potentially hydrogen bonding. If we had the hydrogen bonded to nitrogen, oxygen, or fluorine somewhere in that molecule, it could make hydrogen bonding IMFs to something else. Okay, we notice here that that is a kind of strong attraction. And I put kind of strong because it's at least a permanent attraction. That attraction always exists. For non-polar covalent, we know that that type is London dispersion, and that's a really weak attraction. Remember, those are where we have our temporary dipole moments, and so since they're temporary, they can be broken apart really easily. So then what I did next is I addressed, what if I combine these types together? So you notice here I didn't put an ionic with an ionic because we never see that combination. But what if I put a polar covalent with something else that's polar covalent? I combine the two like types together. Maybe, for example, I put ammonia and water together, both of those being polar. What would happen? Well, since ammonia had original hydrogen bonding attractions, the water has original hydrogen bonding attractions, and I put them together and I still have hydrogen bonding attractions. The strength of what I'm forming is very similar in strength to whatever I started with. So therefore, these are likely soluble with each other. Hopefully remember the statement, like dissolves like. Now, I will warn you, College Board doesn't actually like you to write like dissolves like as your justification as to why two things are polar. They prefer you talk about intermolecular forces and say that the strength of the new intermolecular forces that we formed are similar in strength, or maybe stronger, than the intermolecular forces that the original substances had. So you always want to talk about a comparable strength of IMF types, okay? Non-polar covalent, if I put two of those things together, then they would too be soluble because, again, the strength of the attractions are very similar. Okay, so now let's talk about combining some types together. And the first type we're going to talk about combining is, what if I try to put an ionic compound with something that's non-polar covalent? So when I put those two types together, or try to put those two types together, the new forces that would potentially form are called ion-induced dipole. You notice it's kind of a combination of our names here. Ion coming from ionic bond. Now, induced dipole is not London dispersion. That's like not the same words there. But induced dipole gets that name because the permanent charges on the ion are helping to induce those temporary dipole moments. So we don't call it ion London. That sounds kind of weird. We call it ion-induced dipole. So keep that in mind. Now, here's the deal. Hopefully we know that those induced dipoles, that's very temporary there. Those are weak attractions. So what that means is that overall, this attraction is weak, okay? However, we started out with something that was really strong, and this one was really weak, but I wouldn't trade this really strong attraction for something that's weak. It would be like if I was already dating Chris Evans, I'm sure not going to dump Chris Evans for somebody that I'm less attracted to. Not going to happen. So with that said, you notice that these are insoluble with each other. The weak new attractions won't be able to break the original strong ionic attractions that we had. All right, let's look at the ones on the bottom now. Okay, what we're going to do next is combine ionic with polar covalent. So maybe I put, for example, some sort of ionic salt into water. When I do that, we call the type ion dipole. You notice ion coming from the ionic bond that we had, and the dipole coming from the dipole-dipole forces that we had. Now, here's the deal with this, and this is kind of an awkward category. You notice here that I put kind of strong, and the reason why I did that is because both of these are technically permanent polar moments. Like, they have a permanent attraction to them. Okay, ions have those permanent charges. Dipoles have the permanent dipole moment on them. Okay, so what that means is that these are kind of strong. Okay, now I put often soluble Because it really depends on how strong this ionic bond originally was. I want to actually show you a chart that we looked at on the very first day of this unit. It was in the very first day's worth of notes. It was a chart that had all kinds of different bonds and forces and showed you how much energy those attractions had. So you notice here it said ionic, it would take between 400 and 4,000 kilojoules per mole to break that attraction, or if it was forming, it would release that much energy. Okay, so you notice it's quite a wide range there, and it really depends on how strongly the ionic bond was attracted in the first place. If I come down here to the bottom, first off, you notice I do see hydrogen bond and dipole. So as we know, those are much weaker, okay? But look at this ion dipole range here. I notice that it's 40 to 600 kilojoules per mole, meaning there's a little bit of overlap here between that range and the range of the ionic bonding energy. So what that means is that some ionics might be weak enough in attraction that a really strong ion dipole attraction might be enough to break it apart. Obviously, the dipole and the hydrogen bonding, they'd be willing to break apart, but it all depends on whether or not that ionic is willing to break apart to form the new attraction. So with that said, you notice that I wrote something down here. Remember how we decide if an ionic bond is stronger or weaker? It depends on our lattice energy. Okay, so the higher the lattice energy that I have, that means it's more strongly held together, and that means it's more difficult to break that ionic compound apart. So think about ionic compounds dissolving in water for a minute. Hopefully we remember from last class that some ionics dissolve in water and some don't. It depends. We had this lovely chart here, right? So we had a whole bunch of things that are soluble. Well, the things that are soluble, what that means is that the ionic bond that I had originally is weak enough, and the new ion dipole force that I would form with water is strong enough that we're willing to exchange the original ionic bond to now make those ion dipole forces. On the flip side are things that are insoluble over here. Those are so strongly held together that I'm not willing to break apart that original ionic bond that I had. The new ion dipole forces would be much weaker, and so I'm not willing to trade that strong attraction for a weaker one. So it really does depend on how strongly that ionic was held together. Now, last but not least over here, what if I combine together a polar covalent and a nonpolar covalent? Well, just like we saw earlier, we would combine those names together, and so we take on dipole-induced dipole as our type. Again, the induced dipole coming because the permanent dipole moment on the polar molecule would force those temporary attractions to occur. Okay? However, again, induced dipole, that's temporary. Those are really weak. So overall, this is a weak type. So again, I'm not willing to trade that kind of strong dipole attraction that I originally had in my polar to go form some weaker dipole-induced dipole with something else. I'm not willing to trade my Chris Evans for somebody else if I'm more strongly attracted to Chris Evans. So again, I know my analogy is super silly, but hopefully it gets the point across that I'm not going to trade a stronger attraction for a weaker one. I'm either going to trade a strong for a strong, or maybe a weak for a strong. I'm never going to exchange a strong to go form a weak attraction. Just not going to happen. All right, so with that said, if you flip to the next page, you'll notice a chart where it kind of summarizes all of our new combination types. There's actually one on here that you didn't see on that original page. Obviously, if I have two things that are dipole-dipole, or even one dipole and one hydrogen bonding, if the second molecule is not capable of hydrogen bonding, I would just call it dipole-dipole. So we don't keep that hydrogen bonding part of the name unless both things had hydrogen bonding. If they both had hydrogen bonding, then I can keep hydrogen bonding as part of my force name. Same thing goes for ionic and hydrogen bonding. Like for example, if I had some sort of ionic with water, even though water on its own can do hydrogen bonding, the new thing I'm putting it with is not capable of that, so we revert back to the ion dipole name. Okay, so let's look at some examples here and kind of see how this would work. It says, hey, consider the combination of pentane with heptane. And the first thing it asks me is what dominant type of attractive force must be broken in pentane to dissolve? Well, I see just carbons and hydrogens there. That would be a straight chain hydrocarbon, and hopefully we know that that would be nonpolar. And so in being nonpolar, our dominant type of attraction would be London dispersion forces. Same thing goes for heptane. Heptane is also a straight chain carbon hydrogen, so it too is nonpolar. And so therefore, my dominant type of attraction would be London dispersion forces. All right, so now it asks, what type of attractive forces will be reformed when pentane and heptane combine? Okay, if I put those in a solution together, what will we make? Well, if I put London dispersion and London dispersion together, if I comboed the names together, I would still just have London dispersion forces. Okay, so now it says, are these substances likely soluble with each other or not? Justify your decision. Well, let's think about the strengths here. You know, there might be a slight difference in strength between pentane and heptane due to polarizability, but nothing dramatic. These were both very similar in strength, and I'm forming a new attraction that's also very similar in strength. I'm trading a London dispersion for a London dispersion. So if I'm trading a similar strength IMF for another one, then that attraction is likely to occur. So are these substances likely soluble with each other or not? The answer is yes, and that is because the new attractions formed, are similar in strength to the original attractions broken. If what we break is similar in strength to the new thing we formed, then we're likely to take place. All right, let's look at another example here. It says, consider the combination of lithium bromide with octane. And it kind of has us go through the same steps here. What dominant type of attractive forces must be broken in lithium bromide to dissolve? Well, hopefully we recognize lithium bromide as being an ionic compound. And so that means I would be breaking ionic bonds in order to dissolve it. So then ask what dominant type of attractive forces must be broken in octane. Well, again, I have a non-metal, just carbons and hydrogen situation here. So again, that's going to be nonpolar. And so therefore, I would have London dispersion forces. All right, so then it asks, hey, what dominant type of attractive force will be formed between the lithium bromide and the octane? Well, let's think about this for a minute. From ionic, I would keep the ion part of the name. From London dispersion, we know that that would end up becoming induced dipole in our new combo name. So that gives us ion induced dipole forces. Now, let's think about what's happening here for a minute. We know ionic bonds are really, really strong, right? We're breaking bonds, not just forces there. London dispersion forces, well, those are really insanely weak. Those don't even have temporary polar moments to them. So this new attraction that I'm forming is not all that strong. I'm not going to break apart this really strong thing to go form something that's weaker. I'm not going to break my attraction to Chris Evans to go form weaker attractions with someone else. Not going to happen. So with that said, it says, are these substances likely soluble with each other or not? The answer is no, they are not soluble. And the reason why is because the new attractions are much weaker in strength to the original ionic bonds. Again, I'm not willing to trade my super strong ionic bonds to go form weaker attractions with something else. Not gonna happen. All right, so with that said, the next page has some other examples that are very similar to this, but it also asks you kind of a little bit of a review question in that it wants you to draw a particle diagram that shows what those attractions would look like. So this is a little bit of a review from last class. So this one has sodium chloride with water. This one has water and ethanol. And so what I want you to do is just to take a few moments and see if you can work through this example. So pause the video, go try them out. I'll give you a moment. Okay. Did you go try them out? Did you pause that video? I'm going to guess that you did. So let's go ahead and talk about these real quick. So for sodium chloride with water, I originally had ionic bonds in the sodium chloride. That's an ionic compound. Water originally had hydrogen bonding forces in it. Hopefully those were pretty easy for you to identify at this point. So then when I put them together, I don't call this ion-hydrogen bonding because I don't maintain the hydrogen bonding in the water when it forms the attraction of sodium chloride. So I revert back to the dipole part of the name. I call this ion dipole forces. Now you notice it does say here dominant type of attractive forces. Technically, I would also have London dispersion forces present here. Those are always present regardless of what else is going on. It's just not the dominant type at that point anymore. The ion dipole is the dominant type. So then it asks, are these substances likely soluble with each other or not? Justify your decision. And yes, we would predict that these would be soluble because these new forces formed are similar in strength to the original forces that we had. These were both fairly strong and this is fairly strong. Now, I will warn you, ion dipole doesn't always form. So you may need to double check it against solubility rules. Hopefully we remember that anything with a group 1 salt is soluble. So anything with sodium in it would be soluble. And so that's why we kind of knew that these are likely soluble with each other. However, if you had a different ionic, you may need to check it against your solubility rules just to make sure. Like for example, let's say I had, I don't know, maybe chloride, bromide, or iodide with maybe silver or lead. Those are pretty common combinations to see. Well, those being insoluble, what that must mean is that their original attractions in the ionic compound were stronger than the ion dipole forces that I'm forming. And so that's why those would not dissolve at that point. So then it asks you to draw a particle diagram showing the interaction of sodium chloride and water. And hopefully we drew something that kind of looks like this, where we have our sodium and our chlorine ions. And then we've arranged the water appropriately around them with the oxygen end near the sodium, because we know oxygen end of water is partially negative. And then the hydrogen end around the chlorine, because we know hydrogen is partially positive in the water. Again, you could draw your waters in a space-filling model looking like a Mickey Mouse. I chose here to draw them as Lewis-Dot structures, but you could do that either way. So then on the next one, it says, hey, consider water and ethanol. Now, this one didn't originally ask the question of, hey, what kind of dominant attractions are in water and what kind of dominant attractions are in ethanol? But you could very easily do that first if they didn't present that as part of the question. So I thought through that process and I said, well, hey, I know water has hydrogen bonding. I know ethanol also has hydrogen bonding, so therefore I maintain those hydrogen bonding forces once I put them together. I will warn you, if one of these had been hydrogen bonding and the other had just been dipole-dipole, then I would have just actually called this dipole-dipole at that point. So be kind of careful there. Now this is the dominant type of attraction. technically you also have dipole-dipole, and you also have London dispersion forces. Here, since it just asked for dominant, this was all I needed to address though. So then it says, hey, would you expect water and ethanol to be soluble in each other? And I would say, yes, absolutely. The forces formed, these hydrogen bonding forces, are similar in strength to the original forces that we broke. I had hydrogen bonding to begin with, I had hydrogen bonding at the end, and so therefore those are likely to form. Last but not least, down here it said, hey, in the space below, draw an ethanol and water molecule illustrating the intermolecular attractions that they would form. So the first thing I did is in the dark blue here, I drew in my ethanol. And on the ethanol, I went and identified the partially positive, partially negative end of this. Now we have to be really careful. When I have that OH group here, remember this carbon-hydrogen kind of side of this molecule tends to be pretty nonpolar. So my polar moment happens right here with that OH. So always kind of watch out for that alcohol group on an organic, because that's where you want to assign your partially positive, partially negative. The oxygen would be partially negative, the hydrogen would be partially positive. And really, while I do it in a straight line, technically that does have some bent angles to it, so keep that in mind. So then I want to go draw water attracting to that partially positive, partially negative. Now, since it only said draw a water molecule, you could have drawn either one of these situations. You could have drawn the oxygen end of a water molecule attracting to the hydrogen side, or you could have shown the hydrogen side of the water attracting to the oxygen of the ethanol. Kind of your choice there on which one you drew. AP, College Board, would accept either one of those, so it's kind of a take your pick. You would want to be really careful though to make sure you're showing that attraction with a dashed dotted line versus a solid line, because again, I'm trying to show a force and not a bond. All right, hopefully we're feeling confident with identifying these combination types of intermolecular forces, as well as hopefully we're feeling confident with being able to justify when things are soluble in each other or not using terms relating to intermolecular forces. If you have any questions or need any help, please feel free to email me. Bye, guys.